Is it visible? Oh, I see my own presentation, so that's pretty okay. I presume that it's visible. Thanks for a great introduction, and I'm very happy to be here. Sorry that you have to see the upper side of my of my wardrobe, but that's how it is. I hope it's okay. And as Martin mentioned, we're going to talk about ML and Q#. And first we'll get more into the Q# part, then we'll get into the ML part. So I'll be happy to guide you through. And as I mentioned, the agenda is basically that first I'll talk about Azure Quantum and QDK. I get some terminology straight, and then we'll get into the ML part. And then we'll have some time for the wrap up. And I'm also going to be asking some questions, which are just going to be very, very minor. But if you would like to respond, please feel free to respond in the chat, because I can see it. So I'll be able to know what's the general idea. Okay, so I know that it's not a very standard practice to show the resources on the basically second or first slide, but it will enable you to start your quantum journey. And this session is more of a teaser than anything else, because there's just so much you can do in a session of this length. And what I want you to take from it is the resources. Of course, you'll get the presentation later on with all the links attached. So you'll be able to click on them and do stuff with the links. As you see, they kind of are three main groups, which is learn quantum computing, hands-on parts, and additional resources. And what I want to highlight is if you're not aware of quantum computing, and if you're, first time you're hearing about it in a more, let's say, technical way, those two links, which are at the top of the Learn QC, are the links to Microsoft Learn paths, learning paths, where you can learn fundamentals of quantum computing, like what is entanglement, what is a qubit. If you don't know these things, I'll try to keep it as easy and as low key on this session. And of course, later on, if you would want to get back to it, have some more knowledge about it, learn some more about what I mentioned, it's going to be great to have some knowledge and then get back to it once you know those basic things. Okay, so in philosophical discussions, and I hope it would happen, many more discussions here in real world, is we say that first we need to get the terminology straight. It was like, get our definitions, get to know what we're talking about. So we're going to be talking about three things, which is Azure Quantum, Q#, and QDK. And first, I want to have a short question. Have you used Azure, Microsoft Azure, or any other cloud resources, or did any of you did anything with it or work with it professionally? Maybe you're aware of Azure Machine Learning, which is a service which is inbuilt. I don't know. Some people say that they haven't used the Azure yet. So Azure Quantum is basically a resource which you'll be able to access from Azure Portal. Azure is basically a cloud environment from Microsoft, where you have different resources from virtual machines to some more complicated things like Databricks, Spark clusters, or Azure Machine Learning, which is like a full resource for training your models and deploying them. And Azure Quantum is just the same resource. It's just a resource in Azure that you'll be able to access. It's not available yet, so it hasn't gone to the public yet. So if you're interested in getting this, you can go to one of the links I mentioned in the before slide. Of course, you can also Google Microsoft Quantum Network, and there is a form where you can write as a person or as an organization why you want to join the Quantum Network. And you'll be able to get the access to the quantum computer on Azure, sooner than the rest of people. And what is also important is that the Azure Quantum is probably going to be available later this year. There is no public date available for everyone, so I can't say very much more. And Q# is a domain-specific language for quantum computing. It's just like SQL or HTML are domain-specific language for their domains. That's the same as Q# is just a language. And QDK is a quantum development kit. and it's a full-featured kit for Q# that you can use with standard tools and languages that you know, and you can develop quantum applications that you can run in various environments, including the inbuilt full-state quantum simulator. What that means is that inside the QDK, you have the simulator. You don't need to have a quantum computer, in your basement or on your Azure subscription to run those programs, because QDK has the inbuilt simulator, which can simulate what's, let's say, actually is happening in the quantum computer. Okay, a few more words about the Azure Quantum and why maybe it is good to use it and good to think about using it in the future when it will be available both on like a private level and also like a level of organization. First of all, QDK is open source. So if you want to see what's happening inside, if you want to see what people have built, you can go and join the community right now. You can also help them build the QDK, because a lot of times what's happening are some kind of hackathons or other events that are enabling us to build along with Microsoft team. For example, right now, it's ending because it's the end of October. There was this Hacktoberfest where you can, some issues were raised and you can kind of address them with this hackathon. Second of all, it's security. It's secure, and you're available to, have access to this quantum computer. It happens that you can have your own server, but I think it's going to be quite hard to have an own quantum computer. So that's also a good point. It's a known environment. If you know Azure, if you know the cloud, you don't need to learn anything else. The resource deployment and dealing with resources is the same. And also for development, you can use standard tools that you know and like, for example, Visual Studio Code or Visual Studio, just as it is. When it comes to Q#, as I mentioned, it's domain specific. And these are the two most important things. It's hardware agnostic. So when new hardware comes out, you don't have to, rewrite, change your code or learn a new language, because it's going to be optimized for the new hardware. And you can kind of learn the language now when the quantum buzz, let's say, is in the making. So it's going to be easier maybe for you to play with it and actually do something with it later. And I also have a bit of a, let's say, a tangent about a thing which I consider very important for me when I started learning quantum computing and learning what it is all about, is these are quantum-inspired algorithms. So actually, quantum algorithm, which are actually running on a quantum computer, it's happening, but it's not happening maybe as fast as we would all want, or maybe as fast as we would all need to be using it. But thinking of problems that you have in a quantum way is basically a new tool for your toolkit in problem solving. So if I have an issue, I look at it and I think about it, okay, so for example, if it's an optimization problem, which is very good for quantum, maybe I can use like quantum thinking or a quantum inspired algorithm, which bases on how, qubits, which is quantum bits, work. And I don't really have to have this quantum computer at hand. And a typical problem of that sort is, as I said, optimization is like we can imagine like a ship, two ships and a lot of packages, and we need to sort those packages to have the, the difference between the weight of packages on ship 1 and 2 is minimal. So we're minimizing it, optimization, of course, and we have minimal input and minimal output, and we have a very vast tree of possibilities, growing very fast as we add new packages to it. So that's a sort of problem that we would use quantum-inspired algorithms to solve. Okay, so without further ado, let's get into the demo part and more of a explaining, because as I mentioned, I want to talk about, some quantum stuff. And okay, I know that. Whoop. Great. So What we're going to be doing today with this quantum machine learning library, which documentation is also available to you under in the links that I showed. You can also Google it if you want to look at it now. It's not only it has samples, it has tutorials, it has information about the things that are inbuilt in the library. So you not only can read the code and understand it deeper, but you can also read about more broad view what's in there and what you can find. And okay, so maybe you can guess from the outlook that we have here, we have 3 bottles of wine. So we're going to talk about the wine data set, which is everyone knows it, everyone loves it. And the basic tabular data set that it is, it has some features and it has some samples, sample 1, sample 2, great. We know how it looks, we know how it works. Then we have the class that it belongs to. This is a 3-class data set. And if we have a basic machine learning algorithm, it's funny that we call them basic because so not long ago they weren't so basic, and they're not so basic, still, but we have the quantum now, so we need to call something basic. So when we use the basic machine learning, let's say, for example, neural network. So we have an idea how it works, that we have this tabular data set and we input it into the neural network. So we have the first layer on input neurons. We take the sample, we code, we input the feature 1 value to the first neuron, second neuron, so forth, so on. And then we have the input layer, and then here it goes, all the back propagation, everything is happening, and then the neural network is learning, and we have kind of an idea how it works. Depending on the black boxy, how black boxy is the model that we're using, it can depend how much we know. But when it comes to quantum, it's even more complicated because we have machine learning and quantum. So that's like another level of abstraction. So the big question might be, okay, so how do we input this classical data, because it's clearly classical data set, there's no quantum information here. So how we input this classical data into the a quantum algorithm. And what algorithm we're going to be using is a circuit-centric quantum classifier. And this classifier is available in the quantum machine learning library, and it's already inbuilt, so you don't have to build it from scratch. You just can use it as it is. If you want to read more, you can read how it works, read what's in there. But that's a thing which is given inside the library. And okay, so how does it look like? What does it do? In a very broad sense, as I say a lot of things in here, let's think of a logical gate. We have a couple of logical gates, and they kind of build an algorithm, and then at the end we have some kind of an output. And those, we also have quantum logical gates, which are built out of qubits. So in a normal sense, in a normal logical gate, that's a basic bit. In a quantum circuit, in a quantum logical gate, it's a qubit. And qubit is a quantum bit, which means it's not either 0 or 1. It can be in a superposition state, which means it can be both 0 and 1 at the same time, with the different probabilities of being in those 2 different states. So for example, it can be 40% of a 0, 60% of a 1, let's say, for example. And what we built right now, what we have built, having those, adding those logical gates together, is a quantum circuit. We can think of it as a coroutine of a quantum algorithm in a way. So that's what it is. And we're having different layers of qubits. So as I gave an example with the neural network, we can kind of think that we have the input layer of the neural network where we are, and this, of a quantum circuit-centric quantum classifier. And this first layer is parameter-free. It's just based on the data. So it's just like an input layer at the neural network. We input the data just into this one. And then we have the classification layer, which classifies the information. And then we have some sort of output where we can see and infer the class of a given sample. And okay, so this is pretty easy when we imagine a logic gate, or this. Let's say we have the algorithm and we kind of put it back into the kind of logical space, and we know that if we have a certain sample, we input it into the logic gate, we, certain, let's say 0, 1 sequence, we always get the same output. It never changes. But when it comes to quantum, the output can change. So how we actually use a quantum circuit-centric quantum classifier is we do 3 steps. First, we input the data, which is a classical data, to represent a quantum state. Then we prep the classifier with this data so that the information which is in the data set is shown in the rotation angles of the qubits. And then 3, when everything this is done, we measure. So we get either 0 or 1 in a given qubit. And as I said, if we would have a basic algorithm, a basic logical number of logical gates, we would always get the same output. But with the quantum, it's not the same, and we need to do this n number of times so we have a kind of an idea what's the probability of getting either a 0 or a 1, and we have the information what kind of class, like what's the probability that a given sample belongs to a class 1 or class 0. In the wine dataset example, we have 3 classes, so we need to have like 1 more qubit to tell us about that, let's say output layer. But the basic idea of how it works is just this. We have qubits, we input them into a quantum state with this classical data set. Then we, with preparation of the classifier, that's how it works. And then we measure the output, and we do it n number of times to see what the probability that a given sample is this or that. And of course, after it learns the, I can't say the weights, the rotation angles for, that these rotation angles are, class this type of wine, the other type of wine, or this class number 0 or this class number 1. We can do the same with the validation, and it just works the same. So it bases on some previous information, and it gives us the output that it thinks it should have. But of course, we can measure it a number of times, and we see that it's a probabilistic output when, for example, we know that this we already trained the classifier and we have it ready. So we know that it might be 90% class 0 and 10% class 1 and 0% class 3. So we also have like more information, let's say, about what's the alternative with another classes. Okay, and another thing I want to say, I want to kind of expand on the point that I mentioned before, is that it was really hard to move my mouse. If you're using Visual Studio Code, the only thing you need to have it all, and put write in Q# and write your first quantum algorithm, is if you go to extensions here on the left, you need to search for Quantum Development Kit. Microsoft Quantum Development Kit, and install it. And then, of course, with this information here at the bottom, you not only have the Getting Starting Guide and the Quantum Computing Fundamentals. This is the Microsoft Learning Path that I mentioned before, but also you have the GitHub repository with the whole QDK that you can read through and see how it actually works. So that's the only thing you need. And that's the only thing that you need to install on your local machine to be able to write in quantum. And okay, let's get into the actual repository. And let's talk about that one. Okay. I know that it's not, I see that it's not very pristine, the outlook, but I hope that you can see it just right. Maybe I'll enlarge it a bit. Okay. So basically, as you see on the left side of a tree here, I forked the repository, which is the Microsoft Quantum repository, which has all the samples and all the tutorials and information, with the code from the Quantum Development Kit. That's just basically it, the big knowledge place. And I went to the samples, machine learning, and wine. So that's the example with the wine data set. As you see here, we also have half moons, which is another classical, let's say classic, not classical, because classical machine learning would be not quantum, but classic is like, you know, class C data set. So that's just another class C data set. And what we need to do to run a first Q# program is that we need to have some, clicking it on the screen, which is not what I wanted, to have a place where we're actually going to run our Q# program. Here we have, as you see, training.qs, which is a program which is written in Q#, which is actually what's going on and how everything is getting classified. But we need to have something above it. So we need to have something, a way of running this program on our machine. So as you see, and as it was mentioned before, you can use either Python or C# to write this top-level program to run the functions which are available in this Q# file. So let's go into the Q# file, and I'm going to stop and talk about a couple of things which are here. But what I want you to take from it is that this code is available for you to, you know, also fork or download and do anything with. And you can use this code to build your own, first, build your own quantum circuit-centric classifier. That's a very complicated name. And second of all, you can use this one, which is already ready here, to classify your own data set. Of course, we would need all this input. So I'm actually using a cloud environment because it has inbuilt packages that I need, so I don't need to install them locally on my computer, which I would say that when I was trying to use Jupyter extension on my local computer for this one, because I needed to do something, it super crashed and did something weird. So I switched to this one, which is a very neat way of coding. And let's look into the two functions that we're using into this file, in Python file, which is train wine model and validate wine model. And it's pretty obvious that these are the two functions for training and validating our model. And as you can see, this is just the line where we get the wine data set. So what you can do is, instead of this data set, you can input any data set that you want. Here we take 142 first samples for training. And this is the interesting line. I think this is the most interesting line in the code, which is a classifier structure. And okay, so let's go and see the classifier structure. You can see this function here. As you can see, Q# is not very different from like a C#-ish language. You know, it's a Q#, so it needn't be too far off from this from C#, but it's pretty easy. It has some minor differences when it comes to when we'll follow up. If you go deeper, then it has some maybe bigger differences that you can see here, but it's pretty straightforward. It's pretty easy to understand. As a C# is a pretty, let's say, I think, easy language to use. And as we talked previously, when we talk about what is a circuit-centric quantum classifier actually doing and how it is built, we see that we're having a couple of, let's say, layers, as I mentioned, which are two local rotations, cycle entangling layer, and partial rotation layer. I'm now going to talk about what these are. And as you see, first you have the number of qubits and an axis through which it is actually being, the spin on which axis is actually being input, like added on those qubits. And when I talked to Chris Grenade, and he's a researcher in Azure Quantum Computing, he's actually one of the people who made the QML library. And I talked to him, asking him to explain some things to me that I didn't get myself, and checking with him this session so that he can tell me what are the important information. I also asked him, the classifier structure. Okay, I see that we have those different rotation layers. I know that the feature of the data set are input into the rotation layers, and also the relationship, like the correlation between the features, are input in the entanglement of the qubits. So this is what I know. Can you please tell me, if I have a data set, and here is the data set, how can I build my my classifier to be efficient? And he told me an interesting thing is, he told me that, on this stage, this is kind of a trial and error. what they did is they built this classifier and it yielded the best results. So that's why they input it here, and that's why we're using it in this scenario. But you can change it up. You can change the number of qubits. You can change the number of the access here. On the QML documentation in it, there is like a very short passage where you can read what are the best practices. Like, this is a very, very broad, let's say. So I can call it a best practice. What are why, for example, in a certain example, you have X here and Z here, because it's part of a what's correlation in the data, and that's the best way of when we can do a sort of a gradient descent with the rotation angles. But I tried to change it up a bit with worse results that this is giving me. Of course, this is not a very big data set, so you can't really see that much what's the difference. But I also want to mention that he told me, and that's a very good point, that you need to be aware that whatever comes out of this classifier is going to maybe be worse than your classical algorithm, because we have classic data and we're trying to use it for a quantum problem, which is not a very classical. It's very funny to mix up those words. Saying it differently, basically we use quantum machine learning for things which are connected, as I mentioned before, to optimization. And using the basic data set like wine is just to show how it works and showcase this algorithm. It works pretty well, but it's not the go-to function of this algorithm. And also what is important, it's going to be slow, because you have the whole machine learning thing, and beneath it, you have this full quantum state simulator, as I mentioned before. So you need to be aware that your computer might be a bit slow. That's also a point why I'm using a cloud environment. So I would highly recommend you come here and play with the classifier structure, build your own classifier, and here you'll be able to take your own data and see how it works, see what's up. Also, when it comes to the training options, you can see basic parameters for machine learning that we all know, like learning rate or mini batch size, but also you have number of measurements. This is the point that I mentioned before, which is how many times it is actually measured how many times do we go through encode, prep, measure, and how many times do this thing go on and on. So of course, the more times we do it, the better results we get, but there is this as a horizon above which we cannot go. This is also a good parameter to see and check how it is working, how it changes with the number of measurements we do. And also a default schedule, which is the last important part here. We can see it here at the top. Default schedule is how we take the samples which are in the data set. Here, as you can see, we take all the samples from the 0 to the last one, and we take them one by one. We can take them differently. We can take them, for example, 2 samples for one, and then we will input into the classifier. We would encode 2 samples, or for example, we can take every second sample. So that's kind of also a thing that we can play with, and on this top level, and we can see how it changes up, how it changes the results that we get. Okay. I think I want to get back to the presentation right now. Okay, great. So here comes the question. When do we use quantum? When do we want to use our machine learning in Q#? And there are 3 things. One thing is when we have large feature spaces, then we can use it, because I'm not going to go through the whole proof here, but when we have n features, when we have wait, I think I need to count it in my head again. Yes, when we have a number of features and we need logarithm m to the power of 2 features, qubits, to input those features in, which is, it's logarithmic. So it's gonna, when the feature space is booming, then we don't have, this linear or exponential growth in the number of qubits that we need to have, but we still have a, reasonable number of qubits. Second of all, it's very good in optimization because basically quantum is born from it. The whole idea of quantum computing started when it comes to optimization. And also the problems like chemistry, that's also a very good one, and machine learning, it's still in an early phase. As I told you before, after talking with Chris, he told me that it's very good that as much people are learning and as much people are actually getting into this ML and Q-sharp thing, because as I mentioned, the Hacktoberfest, when there are hackathons happening all over the place, we can make this library better, and we can make the QDK better for everyone who's using it. And that's very important, that if you want to, commit and do something in this area, that's a very good thing, a very nice touch to do. And last, I want to have a very big thanks to Chris Grenade from Microsoft Azure Quantum, who helped me a lot with what's in this session. And I'm also leaving here my email. So if you have any problems, any questions, anything that you want to address, feel free to contact me. If you have some problems with the with the Jupyter Notebook, that's also very welcome. And I'll send you the presentation, I'll send you on the links, and I hope that, see you at some quantum conference,